what we had started with is we had actually talked about conditions of equilibrium. And we have two conditions of equilibrium. And one is the sum of the forces equals 0, and the other was the sum of the torques equals 0. And we had talked about that the magnitude of the torque was going to be F R sine of the angle, because this is a cross product versus our scalar product. And we had talked a little bit about what we were doing in terms of rotational motion. So I'm going to start with, if we start with the torque is equal to RF, making the assumption that the sine of the angle is 1. So this is our maximum torque, okay? Our maximum torque. If I write this out, I'm going to get R is equal mass times acceleration. And we've seen what R times acceleration is, right? And my tangential acceleration is R alpha. So my tangential acceleration, so if I put in here, I'm going to put in an R alpha, and then I get something that looks like mr squared alpha. So we know that the torque is going to be proportional to the angular acceleration. And we have this value that's an mr squared. Okay? This we're going to define as a moment of inertia. And the total moment of inertia is going to be the sum of all of these individual point masses at that distance squared. So if I look at this, and let's take a disk here. So if I have a disk, and we even talked about this on Wednesday, that if I'm rotating this disk about a center point, I'm going to get one thing. If I'm rotating this disk, say, around a line like this, I'm going to get something else. All right, so in this case, I'm rotating it around this line. In this case, I'm rotating it around its center point. And we even showed the chart that's in your chapter. Okay, we even showed the chart that's in your chapter. But if I have, let's say I have a mass that's out here, and I'm rotating it around my point like this, if I have a single mass, my moment of inertia is going to be related to mr squared. But if I'm rotating around a place like this, I'm going to have this little incremental mass that's going to have a mass and an r squared. I'm going to have another one out here that's going to be a different r and a different mass. I have one that's going to be over here, and that's going to be an r with a different mass. And so my total moment of inertia for this disk, which we're going to define with the big letter I, is going to be the sum of all the individual little masses that I have to go through. Now, for those of you who have to take calculus, this, of course, is algebra-based physics. Algebra-based physics says we're going to do a little individual sum. Even calculus-based physics says we're going to do a little bit of individual sum. So if I look at that example that's in my text, where I have a baton here with different masses, and we talked about if I'm rotating it about the center point where this is going around and this one's moving around like this, that's different than if I'm trying to balance it off of a point here and I'm rotating it around that way. So I get some differences, But in these, I can take each one of these as m1r squared, and this is m2r squared, and this is m3r squared, and this is m4r squared. And if I do this sum of the individual masses, what this is going to look like, if I'm calculating its moment of inertia, I'm going to have m1r squared 1 plus m2r squared 2 plus m3r squared 3 plus m4r squared 4. Well, if I'm rotating it from the perspective that this is rotating around, so I'm rotating it, I have a mass here, a mass here, a mass over here, and a mass here, and I'm going to rotate it this way. My r is the distance between this axis and there. Well, guess what? That means m1 is 0 because there is no distance away from my axis. m2 is equal to 0 because there is no distance away from my axis. And so this is going to be r3 and this is r4, and we're going to say that r3 is equal to r4 for the purposes of this baton. And we're going to even say that m3 is equal to m4. So I'm going to have now m, because those masses are the same, r squared plus mr squared is going to give me 2mr squared. Because, so for rotating it this way, we're talking about this direction, I'm going to get a moment of inertia that's 2mr squared. Now, if I'm rotating it such that it's rotating around a plane this way, things are going to be different. So we're going to say R3 is equal to R4, and I'm going to get R1 and R2, and R1 is going to equal to R2, but they're not equal to R3 and R4, but M1 is equal to M2. This time the moment of inertia is going to be a little different. Okay? This time the moment of inertia is going to be a little different. So I'm going to call M1 is equal to M2, I'm going to call it M1, M3 is equal to M4, I'm going to keep the M3, I'm going to keep the R1 and the R3, okay? I'm going to keep the R1 and the R3. So now I is going to be equal to M1 R1 squared. The second mass is M1 R1 squared. And for those of you who use Chegg, I don't mind you guys using Chegg, you just have to understand what you're getting when you use Chegg. This is really M2 R2 squared. Chegg will just go ahead and write it like this, and you're going, well, why am I doing the same thing? Because they're leaving this step out. So it's not necessarily clear why I get that part. That's where things get confusing in Chegg, and you got to understand, well, the reason I can write this out again is because M2 and M1 are the same, and we kept it as M1. R1 and R2 is the same, and we kept it as R2. So now I'm going to do the other side, and that was M3 R3 squared plus M3 R3 squared. And this comes from the fact that M4 and R4, M4 and M3 are the same, so I'm going to use it as M3. R4 and R3 are the same, so I'm going to use it as R3. So this time I'm going to end up with 2M1R1 squared plus 2M2R2 squared. And that's for the case that I'm rotating around like this, with my other baton having my bigger masses sitting out over here. So it does make a difference how I'm going to do that rotation. And for those of you who want to look it up in the text, I think it's going to be pretty darn close to example 9, and it's called the baton twirler example. So that you can actually go in and look at it, and they actually put masses on everything. But we get different moments of inertia, and it's going to be based on different things, based on different configurations and geometric configurations. Now, let's look at this, because we've talked about it a little, but this is the chapter where it really comes home to roost. I've got this, and one of the things that when we did F was equal to G M1 M2 over R squared, we talked about this concept that things are going to behave via the center of mass. Things are going to behave via the center of mass, and where that comes into play, and we've all done it, and I think I even demonstrated it a little bit. So I have a tabletop here, and I'm going to put a book over it, and I can have this book hang across the edge as long as the center of mass is supported by the table, because I'm going to have the force, the normal force, and the force due to gravity. As long as this is centered over the table, it's going to stay on the tabletop. Now, the instant that it's no longer centered over the table, I give it a little bit of a push, and this is now over there. There's no supporting it, and this is going to rotate off and fall off the table. And we know we can play with this because I can do stacking of books. And I can stack a whole lot of books, and ultimately I can even stack a book out here where its individual book is off the edge of the table, and the whole stack of books stay there because the center of mass for the whole system is still above the table. This individual book may not be, but it's being supported by this book, which is being supported by this book, which the whole system is being supported by this. And I don't have this top book fall off. That's why we get really strange things like this. Good old Wile E. Coyote and the Roadrunner, right? We get this big, huge boulder over here, and we could actually have what looks like to have most of the boulder sitting out over here. But this thing is balanced because its center of mass is still over the edge of the cliff. And that's where we call it center of mass. It's wherever the mass is going to be acting, and gravity acts through the center of mass. And we even talked about it when we did the human loop-the-loop. We saw the human loop-the-loop. The trick to that problem wasn't being able to do the speed that he needed in order to get there. The trick to the problem was his body mechanics. The trick to the problem was his body mechanics, because remember what he ultimately had to do, and he had to kind of position himself. So there's most of the body, and there are his legs, right? Again, I'm not the best artiste in the world. But the trick was to keep his body, the center of mass of his body, in a pretty decent, manageable way in order to go around the loop. And if you watch it, the part of it is the loop isn't much bigger. And that's something they never ever mention, because when he stood up in the loop, his body was such that he was probably trying to keep the center of mass towards very close to the center of the loop. Because you look at that loop wasn't all that tall. And you look at his size versus the size of that loop, that's exactly what they did. They did it such that he could keep his body mechanics, such that he could keep his center of mass pretty much around that point, and then he could rotate around. So the trick to the problem was actually the size of the loop, more so than whether or not he could achieve the velocity. Now, for some of them, it's achieving the velocity, and those of us who played Hot Wheel cars for gazillions of times, you know, the trick really is to get the velocity, right? And we did the problem, right? We did this problem, so we did the loop-to-loop, and how high did we have to have the little marble or the Hot Wheel car or whatever in order to get the loop? So we get this center of mass, we have to look at that center of mass. So we can calculate centers of mass. Okay, we can calculate centers of mass. So I can have an object, so I've got an object here, and I've got an object over here, and I've got an object over here. And we're going to position this such, I'm going to give myself a coordinate system. Okay, for the sake of argument here. So this one is going to be positioned 3, 3. This one is going to be positioned at 1, minus 1. And this one is positioned at minus 1, 3. And we're going to give them that mass 1 is equal to mass 2 is equal to mass 3. Okay? Mass 1 is equal to mass 2, mass 3. I just want to get it in the exact form of the way your book does it. Now, intuitively, if I knew about this and I'm trying to balance it, where do you think, and we're balancing it, so these are 3 things that are sitting on a tabletop. Let's put it on a fictitious glass plate that has no mass. And I want to put my finger under that glass plate such that this thing is perfectly balanced. We know all 3 of those are the same masses, and intuitively we know kind of where we want to position it, right? I want to put my finger such that I'm going to balance it. Intuitively, I know it's probably, since all 3 are the same masses, it's probably going to be at a point like that. Because we've done it. We've played the gravity game. By definition, we can do this as x center of gravity or x center of mass. Center of gravity, center of mass, same thing. One is just we're talking about gravity, one was talking about that. Or I can do this with a bar across the top to give it that. This is going to be equal by the sum of the individual masses. That's when we're going to use an I, times its x position divided by the total sum of the masses. Okay, I can do it for my individual y as well. And if I need a z, I can do it for z. So our total mass, if M1, M2, and M3 are the same, our sum of our masses is going to equal M1 plus M2 plus M3, which is just going to give us 3M, right? So I've got my subtotal masses there. So now I can actually do the individual, calculate where the center of gravity is for this system by doing the sum of the individual masses times its radius, or in this case its x position. So I've got mass 1 times its x position, which is -1, plus mass 2 times its x position, which is +1, and mass 3, which is its x position, combined. These and M1, M2, and 3. So now I get -m plus m plus 3m Did I do that? -1, yeah, I did that right. Plus 3. So I'm going to get -1, 4, so I end up with 3m, right? And my x center of gravity, that's why I said something doesn't look right here. Because this is telling me my x is over here.
That's the y position, though.
Well, it's telling me my x is going to be on this on at 3 over here. If these three are all the same, this is my minus, my -1. That's giving me 3m divided by, oh, no, it's not, you're right. Oh, yay, there's something right. Because I forgot to do this. It's been a long week, guys. So it's going to be over here at 1. It's going to be on this, it's going to be on this line here. Because my x center of gravity is the sum of the mx's divided by the sum of the masses. And in my head, I was just dividing by one mass instead of 3. It's been a long couple of weeks. So that's 3m, so it's going to tell me that it's on this line, which we intuitively knew. That's why I was going, something just wasn't working right. Now if I do the y, my sum of my masses and the y is going to be, this one is 3m. The next one is -1m, and the other one is 3m. So this time I get 6m. So if I do my y center of mass, that's going to be my 6m divided by 3m, and it's going to give me 2. And it puts my center of mass where we expected it to be, right there. So for individual masses, this becomes just a problem in plugging in, checking the numbers. Now, if I do an entire disk, there are tables that will actually tell you where the center of gravity of a disk is. And this is what's really fun, okay? This is what's really fun. Because we can do a lot of calculus in our head. We can do an awful lot of calculus in our head, right? Where's the center of gravity of that disk? We know if it's a solid uniform disk, we know it's in the middle. Okay? If it's a solid uniform disk, it's in the middle. Even if it's a bowl, we know it's in the middle. You know, if we've got something along those lines, because we know that the center of mass has to lie on axes of symmetry. We know that the center of mass has to lie on axes of symmetry. So I know that if I have a bowl, it's still going to be on the axis of symmetry. If I have we know it's going to be, at least in the xy plane, it's going to be in that middle. because I've got to have half the mass on one side, half the mass on the other. So we do an awful lot of head calculus all the time. Now here comes another fun part. So where's the center of mass of this object? We got a donut. Where's the center of mass?
It's in the center still.
It's still in the center. The center of mass doesn't physically have to be on the object. That's why when I said this one, let's talk about as if these three things were on a clear massless glass plane, we know where to balance our finger. But the center of mass doesn't have to be on the object itself at all. It's still going to be in the center. Because we've seen it, we do it, and we do it to our advantage. So we all have seen these things, right? I've got a big object here, and I've got this down here with a little object, and then I got something that comes down here, and these have objects that are hanging off, and this has another object that's hanging off, and we do these things, and we balance it with something that looks like this, and this is the string that's connected to the roof, and the center of mass for that object is going to be under where this is, and it's probably not going to be physically on my mobile at all. The center of mass of this thing isn't going to be even physically on the object at all. And we do it all the time. So I have my pin, right? I got two parts to my pin. The cap side is going to be heavier than the other side. I can actually do it, and let's see if I can be steady enough today, which may or may not necessarily work. I can go in here and find the center of mass, and we can find it empirically. That's just what I did. We found it empirically. At least for the distance across this side. We also know where the center of mass is for the other two coordinates. Because this is symmetric, it's going to be on the axis of symmetry of the device. And because this is also symmetric, we know it's going to be halfway through the pin. So I can actually pinpoint, pun intended, I can actually pinpoint where the center of mass is on both the X, Y, on all three, the X, Y, and Z directions. So we can use that to our advantage. Okay, we can use that to our advantage. Center of gravity and center of mass are fairly consistent. But if I also wanted to do it this way, so this time I want to use R, so I've got my three masses. Okay, I've got my three masses. I can also look at it in terms of this is an R, this is an R, this is R1, and this is R2. And we know how to calculate this. So let's say we found our center of gravity, and our center of gravity is located at 0.6 meters and 0.6 meters. And this is positioned at 0 and 0.9 meters. Okay, so I don't have my picture drawn, just nice and peachy dandy. But we can find what R is. R is going to be the square root of the difference between my 0.6 minus 0 squared plus my 0.9 minus 0.6 squared. This is going to give me the square root of 0.6 squared plus 0.3 squared. And if I do that, R is going to give me 67 meters, or 0.67 meters. And now I can find my moment of inertia, because remember, my moment of inertia is going to be the sum over each end of these individual R squares. So once I find all three R's, I can find its moment of inertia. I can find its moment of inertia. And that's going to come into play and become very important. So one of the classic problems that we do are these. So I have a solid cylinder. Okay, old-fashioned wishing well. On that solid cylinder, I've got a string and I've got a bucket that's coming off of my cylinder. So if I'm looking at it on the end, I have a mass. I can look at it this way. I have a mass that's acting R distance away from my cylinder. Now we're going to be given that the mass of the cylinder is going to be 3 kilograms. The radius of the cylinder is going to be 0.4. And it's going to be used to raise water or coal or whatever out. The mass of my bucket, we're going to say, is 2 kilograms. We want to find the tension in the cord, okay, and the acceleration of the bucket. Okay, and the acceleration of the bucket. Well, and this, what we're going to do is we're going to let the bucket pull, because we know what happens here. If I were in equilibrium and I've got the brakes on, this thing is going to stay put. But as soon as I let go, this is going to fall down, right? That's going to fall down. So if I look at my bucket by itself, because we've done this one before, there's the tension in the rope, there's mg, and we're going to say that the acceleration goes down like that. My summation of my forces is going to equal mass times acceleration. And I got the tension in the rope minus mg, and we've seen this a few times. Think elevator. We did that elevator problem. But now I've got a rotation in the system, so I'm also going to get a summation of torques. And my summation of torques is going to be I alpha, my rotational motion, okay? And the torque in the system is what's happening associated with my rotation here. And I'm going to end up with the summation of the torques is also going to be the tension minus the radius that's going around the circle. And the reason it's negative is because we're going clockwise. Remember that we say this is positive, this is negative. So I've got a negative, and we're doing our torque here because here's our torque. This is my force. This is my radius, and we're going to use capital R. I can look these up, and for a cylinder, it's going to be mr squared divided by 2. So I'm going to get mr squared divided by 2. Alpha is going to be minus tr, but alpha is also RA. So I can plug that in. So now I have an equation that looks like this. I get MA is equal to T minus MG. This comes from my summation of forces. I get mr squared 2 RA for my alpha is equal to minus TR, and this comes from my summation of torques. Now for you architecture design majors, for you mechanical technology majors, which there are a few of you guys in here. It's usually my Monday night class that has my construction technology guys in it. These two things, we play with it such that we get F is equal to 0 and F is equal to the torques for equilibrium. And this is the science of statics, i.e. I'm just keeping everything in equilibrium. This part where we now have the rotation and the motion, this is referred to as dynamics. So for your mechanical technology guys, you do both statics and dynamics. For your architectural people, we want it to be static. We don't want our buildings to move. Right? We don't want our buildings to move. You know, what Frank Lloyd Wright's Falling Waters and Frank Lloyd Wright's a couple of other of his designs were all about doing the architectural effects like this, but in order to keep the building static. Frank Lloyd Wright did not figure out, however, to make them comfortable. Anybody who's ever been to Price Towers, it's the most uncomfortable feeling building on the face of the planet. Now, he did have a protege who did make them comfortable, which is really great. It was actually Herbert Dow, the family of the Dow chemicals. He was actually a Frank Lloyd Wright protege. So we can rewrite this now. So I'm going to rewrite it. So I got MA is equal to T minus mg. I now have mr3 divided by 2a is equal to minus tr. I'm going to divide both sides by r on this one. So I get mr squared divided by 2a, and I get minus t. This gives me one equation, this gives me two equations. I now have two equations, two unknowns. If I go ahead and solve for t there, I get t is equal to ma plus g. These m's are different. This is the mass of the bucket. That's the mass of the cylinder. So I can plug that into the equation, and so I get mr squared 2a is equal to ma plus g. I'm going to solve for a now, so I'm going to get mr squared 2 minus m a is equal to mg. Mg is now mg divided by mr squared 2 minus m is going to equal my acceleration. And if I know the masses, which I do, this becomes, we said that the mass of the cylinder, the mass of the bucket was 2, gravity is 9.8, mass of the cylinder is 3, the radius of the cylinder was 0.4 squared divided by 2, minus the mass of that, and we actually plug that in to calculate it. A works out to be 5.6 meters per second squared. We know it's going down. Plug in for tension, and tension will equal 8.4 newtons. And I'm pretty sure there's a homework problem that looks an awful lot like the well problem. Okay. I gotta get it through a couple other concepts so that you guys can get your homework done. So let's start with kinetic energy. Let's look at our system that way. So kinetic energy is equal to 1/2 mv squared. We know that V is equal to R omega. So now I'm going to put in 1/2 m R omega squared. This is going to give me 1/2 m R squared omega squared. That looks familiar, right? This becomes 1/2 I omega squared. So for a rotating object, my kinetic energy is going to look like this. For a rotating object, my kinetic energy is going to look like that. Go back here. That's gonna do it. Okay. Momentum is mv, but if I use the R omega, I'm going to get mR omega, and this is what's known as angular momentum. We have conservation of energy, we also have conservation of momentum. Okay? Conservation of energy, conservation of momentum. We also can do this make sure I get it right, because I am not. We're also going to define angular momentum because we also have the spinning object. We're going to define it this way. Okay? We're going to define it that way. This is what's going to be angular momentum as well, because I've got rotation. I'm not going to do it that way. I'm going to do it this way. So we're going to get that as our definition. And that explains our ice skater situation. I've got long arms for my ice skater. And we have it there. So if we do this from conservation, in this case, R is going to be from here to here. We're going to make that 0.5. From here to here, we're going to make that 0.25. And if I do this, I'm going to equate my person as a cylinder, and we can do I is equal to mR squared, where this is the mass of my skater. We're changing the radius, and so in this case I'm going to get I is equal to, and I'm going to have my skater be 50 kilograms. We're going to get 50 times my 0.5 squared, which is going to give me 12.5 kilograms meters squared. And for my I2, it's going to be my 50 times my 0.25 squared, and that gives me 3.13 kilograms meters squared. But my angular momentum before has to equal my angular momentum after, because I have conservation of momentum. So I1 omega 1 is equal to I2 omega 2. If we start out with a spin that's 6 radians per second, we want to know what it is when we put in our arms. We get our 12.5 kilograms times my 6 radians per second. This is going to be divided by my 3.13 kilograms meters squared. Kilograms meters squared. Those units cancel, and I stay that way using these numbers. I get something that looks like 23.96 radians per second, which is going to give me about a 24 radians per second. So that's my conservation of angular momentum, which allows for the various spins. So let's go back and define that angular momentum where I messed up. So summation of forces is equal to mass times acceleration. Summation of torques is going to equal I alpha. Okay? Summation of forces is also equal to a change in momentum. Summation of torques is a change in angular. This is summation of momentum with respect to time. This is an angular with respect to time. So if I do it this way, I'm going to get I alpha is equal to I change in angular velocity with respect to time, and I'll get something that looks like I omega minus omega naught with respect to time. And then I can get that we define our L as I omega. I put in my I, which is mr squared omega. But omega, or r omega is equal to v. So omega is equal to v over r. I can put in a substitute here. I get mr v over r. I get mrv, which is the one that I had originally put in. But we're just going backwards for it. And this is looking at it from a tangential view. So that we can go back and forth. Okay, so we did our bucket problem. Okay. So what we're going to do is we're going to do the merry-go-round. So here's my merry-go-round. Radius is going to be 2 meters. It's going to be rotating at a speed of 0.25 radians per second. Initially, the merry-go-round is going to have a mass of 900 kilograms. So it's one of those good old-fashioned steel merry-go-rounds. Okay? And we've done it, at least most of us have. So we're a kid, we're running around, we've got the merry-go-round going like this, and then what do? We jump on the merry-go-round, right? That's what we do. Okay? We jump on the merry-go-round, and where I'm going to jump on the merry-go-round is I'm going to come in and I'm going to jump on the merry-go-round such that I'm going to be 1 meter from the center. So I'm going to manage to land halfway in between. And we want to find out what the new speed is. Okay? I want to find out the new speed. So we're going to do the momentum before has to equal the momentum after. Now, in the momentum before, I have I omega before. It's got to equal I omega after. But this I and this I aren't the same. This is the before and this is after. Because the I before is just my disk, and my disk is 1/2 the mass of the merry-go-round, the radius of the merry-go-round squared. My I after is going to be the disk plus wherever the kiddo is. And we're going to give the mass of the kiddo 30 kilograms. Okay, we're going to give the mass of the kiddo 30 kilograms. So in this case, if I plug in this number, I get 1/2 900. R is 2 meters squared. That should be about 1,800. This one is going to be 1,800, but now I have to add my 30 kilograms at 1 meter squared, so I get 1,830. So now we get 1,800 times my 0.25. It's got to equal my 1,830. For the after, that's what I'm solving for, so I get 1,800 divided by 1,830 times 0.25. Gives me 0.246. So we get a drop. But that's not what the merry-go-round does, right? That's not why we call it a merry-go-round. Because what usually is happening, I'm the little kid here, we got the big kid sitting out on the end, right? We get it really, really going and the kid jumps off. So let's do that calculation. Okay, so let's start with, we're going to use this as the before. Okay, this is the before, and that's the after. When we do that, we get the difference. That looks like this. If the kiddo, if the merry-go-round is going at 0.25 radians per second, and this comes off, so we had calculated that I before is going to be the 1,830, which is equal to 1/2 mr squared plus the mass of the kid, wherever the kid is sitting. And now the mass after is going to be the 1,800, because that's just the 1/2 mr squared. The change is going to be the 1,830 divided by the 1,800, so this is the omega after, or before, is equal to the omega after. So we're going to speed, it'll have an apparent increase, well, it'll have an actual increase in its angular velocity, because somebody jumped off. Okay. So let's say you're working on the Coca-Cola bottling line. Bottles are going to enter the machine at an initial omega equals 0 and a velocity equals 0. We've got, and what happens is we have it coming in and we're going to go around the curve. So this has a radius r. So we got the bottle coming in and we got the bottle coming out. And we're going to say that if at 90 degrees, so when it comes out, it's going to have, we're going to have a change in angle of pi over 2 radians or 90 degrees. And when it leaves, the velocity tangential is going to be 0.2 meters per second. The radius is 0.3 meters. We want to find omega final, the angular acceleration, the centripetal acceleration, and the tangential acceleration. Well, velocity tangential is equal to r omega. Okay? And omega final is going to equal the velocity tangential divided by r. We're given the velocity tangential 0.2 meters per second. We know r, it's 0.3. This gives me 0.67, that's in meters, 1 over seconds, or 0.67 radians per second, or radian seconds. Since I've got v tangential, I can calculate centripetal acceleration. That's just v squared over r. Let's try this again. That's going to give me my 0.2 squared divided by my r of 0.3. And that gives me, when I plug all that in, the 0.13 meters per second squared. I want to find omega final, so omega final is squared is equal to omega initial squared plus 2 alpha change in angle that's going to give me my change, or to find my alpha. I want to find alpha. This was equal to 0. So alpha is going to be omega final squared divided by 2 times the change in angle. We already figured out the final, and that's my 0.67 squared divided by 2, and I can do pi over 2. And that's going to give me 0.14 radians per second squared. AT is just r alpha, so that's going to be 0.3 times my 0.14, and that number gives me 0.043 meters per second squared. So hopefully you've got all of the theory that you need. But this is, remember, what works out really, really well is in your text. In your text, you've got your summaries. And your summaries are really going to help you out. And then it's got the other parts of it there. So I will see you all on Wednesday. If you need me to set up a Zoom to help work some problems, I will. Email me on that. I didn't do a sign-in sheet today over here. That's what you were looking for. And then I'm disappearing off the Enid campus here